In this video, we'll be talking about the strengths of acids and bases. So in grade 11, you primarily learned about acids called strong acids and bases called strong bases. And the idea with strong is that strong acids or strong bases, they ionize completely or dissociate completely in water. So they dissociate or ionize 100% in water. Again, for acids, we say ionize rather than dissociate because they don't really exist as ions. And they become ions when you put them in water, but it's almost like saying they dissolve, but we say ionize to be more specific. And when they do that, they produce hydrogen ions, and the idea with strong acids is that they're so far towards the right side that we say it is reacted to completion. So all of the acid that you throw into water will become H plus or H3O plus, for example. So here we have an example. We have HA plus H2O produces A minus plus H3O plus. So this acid would give the H to the H2O to become A minus plus H3O plus. Notice that there's a one-way arrow there, and that's because there is no equilibrium essentially. If there is, it's so far to the right that it doesn't reverse itself. So all of this is converted to H3O plus. So it's 100% ionization. You could also sometimes write it like this, so HA, AQ, and then you can put this H plus here, AQ plus A minus AQ, and the main point is that there's a single arrow, and essentially all this is converted into this here. There's no more of this HA present. It's all converted into H plus and A minus 100%. So these are actually the strong acids you need to know. HCl, HBr, HI, HClO4, HNO3, and H2SO4. Those are your strong acids, and I'll show you how you know they're strong acids later, but understand these are the strong acids. And so an example here would be HCl. So if I had HCl and I were to put it in water, H2 plus H2O here, I know it's a strong acid because I memorized my 6 strong acids, 1, 2, 3, 4, 5, 6. I'd make a one-way arrow. Because HCl is an acid, it's going to give away the H and become Cl minus AQ, and then the water will be converted to H3O plus. But at the end of all this, there's no more HCl. All of it, 100% of it, became this stuff on this side. You could have also done this, so H, Cl, AQ, and you can just make a one-way arrow to show that it becomes H plus AQ, and then Cl minus AQ. But it's 100% ionization, so all of this is converted into this there. Whereas a weak acid will not ionize 100%. So a weak acid does not ionize 100%. It only partially ionizes. Partially ionizes in water. So what it'll do is it'll produce some hydrogen ions, or hydronium ions more specifically, but there'll still be some of the weak acid left. And the way you would signify that is that you actually have an equilibrium. So the equilibrium actually lies more to the left side, and you don't have as much H plus being produced in solution. It's a reversible reaction as well, so we're going to have our double arrows there. So here's our example. It looks very similar to what we saw above. It's just the HA here. That's the acid. We'll donate the H to the H2O to become H3O plus and A minus, but notice we put a double arrow here. So if we had, let's say, HF, AQ, plus H2O liquid, we know this is a weak acid. So essentially anything that's not one of the strong acids I mentioned, the 6 strong acids, it's going to be considered a weak acid. So HF is considered a weak acid. It's often mistaken for a strong acid by students. Just know it's your weak acid. A lot of carboxylic acids are weak acids. We'll see some examples of those as well. But we would draw a double arrow to indicate that we have an equilibrium. And HF would lose H and become F minus AQ. and then the water would gain H and become H3O plus AQ. But the main point is that you have an equilibrium, and not all of this is converted into this. So you still have some of this stuff, some of this HF behind, left behind. So here we'll analyze a little beaker to show you a strong versus a weak acid. So let's say that this was a strong acid that we threw into this beaker. You can see that we threw it in, it's all HA, but then after it dissolves, you'll see all of it became H plus and A minus, H plus and A minus. It's all separated now. So there's no more HA. It's all gone down to 0, and all of it's converted to H plus and A minus. It's 100% ionization. Whereas if this is a weak acid over here, you'll see that we have, again, we put in the HA, but notice that there's still a lot of HA left over, a lot of HA left over here. And only some of the HA has separated into the ions. So you'll see there's a big chunk of it left over, and then a little bit is ionized. So that makes this a weak acid. Strong acid here, weak acid. Very small percentage of ionization. So the general rule is that when you have a weak acid, you're going to have less than 100% ionization, very small equilibrium. When you have a strong acid, it's 100% ionization and there's no equilibrium. Now, or there is an equilibrium, but it lies so much to the right, it's not reversible. For weak acids, because you have an equilibrium, you can actually have a K expression called a Ka, an acid ionization constant. An acid ionization constant. And so it's essentially the equilibrium constant for the ionization of an acid, and specifically a weak acid. So let's say you want to write a Ka for a weak acid. Well, what you would do is you would first write out its reaction with water. So we have HA, AQ, so let's make that our weak acid, plus H2O, liquid. We'll put our double arrow, and we're going to put HA lost an H, so it becomes A minus, plus H3O plus AQ. And so it's the same rules. You have to make sure everything's balanced. You got 1H, 2 H's there, so 3 H's, 3 H's there, 1A, 1A, and then 1O, 1O. And so we're just doing products over reactants, raised to the power of their coefficients, but they're all coefficients of 1 here, so just make sure it's balanced there. So we're going to have our A minus multiplied by the concentration of H3O plus over HA. So essentially you have the conjugate base over the acid, okay, multiplied by this H3O plus over here. And that's how you would find the Ka expression for a weak acid. We're going to come back in a minute and take a look at the Ka table, which will be provided to you in your references for assessments and for labs. So let's try this example here. Try to pause the video and try it yourself. Write the Ka expression for the ionization of the weak acid HF. Start by writing an ionization equation. So at this point you've tried it, and now you're just checking your work. So your first step is to write the ionization equation, knowing that HF is a weak acid. We're going to make it react with water, because when you're ionizing, we're going to assume that we're in a solvent of water. We're going to put our double arrow because we know HF is a weak acid. We're going to get F minus because HF gave away an H, plus H3O plus. Now we're going to write Ka is equal to the concentration of the conjugate base, F minus, multiplied by the H3O plus over the acid, HF. Now notice that in both these circumstances, I did not include water. And actually, there I made a mistake. You're probably noticing that as you were doing the video, water is not aqueous, water is simply liquid. So in both these circumstances, I did not include water. And that's because water is a liquid, so the concentration is not a thing, it's constant, which means you don't include it in your equilibrium expressions. So we do not include water in the Ka expressions when we do that. So let's take a quick look at the Ka table over here. So if you click on that link, you'll have access to it. So here's your formula book, and you've received the big booklet at the start of the semester, or you received some data. And so if you scroll down here, there's a KSPs, and this table here has your Ka values. So you'll see you have the acid name over here, the acid formula over here, and in fact you even have the conjugate bases over here. And what you'll notice is you have the Ka values here. And so you'll see that these are all the Ka values provided here, and then some Kas are just listed as very large. And what you'll notice is all the very large Kas are the strong ones, the strong acids. So your strong acids have Kas that are so large, meaning they favor the product so much, you have a big product numerator over a small reactant denominator, that it's not really worth to calculate a Ka for that and to say there's an equilibrium. And I said there were 6 strong acids, so if we look here, H2SO4, there's 2 Kas, and we'll see why later, but you'll see that one of the Kas is very large. And you can probably predict why there's 2 Kas, H2SO4. Think about that. And think about if both H's are likely to be given away as easily. Okay, so you can use this table here. You'll notice this table is organized by monoprotic and polyprotic acids. So monoprotic acids, we'll learn later on, give away 1 H, and polyprotic acids give away more than 1 H. Polyprotic, more than 1 proton. Monoprotic, 1 proton. This table also has Kb values, because we're going to learn that bases have Kb values as well. So in this video, we learned about strong acids and weak acids. We learned how to write equations for the ionization of weak acids with a double arrow. We learned how to write Ka expressions for weak acids, and we saw how to use the Ka table for acid ionization constants. A little reminder that the larger your Ka, the stronger your acid is going to be, because what that means is that you favor the products more, and that means that you're essentially donating H plus more readily to make more of that H3O plus on this side. And also, for the same reason, the smaller the Ka, the weaker your acid is going to be. In the next video, we're going to take a look at strong bases and weak bases, and essentially see a similar concept, but just from the perspective of bases.